Hello physics students. Welcome to Gauss's Law Lab 2. You'll find a PDF of this document, Gauss's Law Lab 2, in our Google Classroom stream. At this point, if you wanted to print out pages 1 and 2, you're welcome to. If you would find a hard copy more convenient for reading when you're doing analysis, you're welcome to do that. Or you could just look at the instructions on a screen. But the rest of the lab, which is another 6 pages, those you need to print out because those sheets you'll be doing your analysis on, you'll be writing down your data, and you'll also be answering the questions at the end. And there's some diagrams involved, so most convenient to print these out. All right, as I said with Gauss's Law Lab 1, Gauss's law is most often used in physics to derive the electric field around a certain set of charged objects. But to do a lab where we calculate the electric field in theory and then measure the electric field with equipment, we don't have that equipment here. What we have are these multimeters which measure voltage. So we're going to be indirectly seeing how our data matches our theory, because remember, you can find the voltage or potential from the electric field if you know the electric field by doing negative integral of electric field dx from one x coordinate to another. That gives you the voltage along that path. Or if you have the voltage function along a path, you could do negative derivative of that, and that gives you the electric field expression. So we'll be using those to take our voltage data and compare it to electric field data of Gauss's law, the theory. Okay? So the equipment is very similar to what we used in Gauss's Law Lab 1, but this time the conducting board is colored in a different shape with conductive ink. You could, as you could see on this screen, we have 2 circles here, and these are not cross sections of spheres. So we're not studying a sphere here and a sphere there, because the paper forces the electric field to vary in a 2-dimensional plane. It doesn't allow it to then spread out into 3 dimensions this way or that way. So when you force electric field to only vary in a 2-dimensional plane, you're actually studying, or you have involved objects that are cylindrical, okay? And then as you move in this direction, the electric field actually doesn't vary. And so again, that's cylindrical symmetry. So what I have is a cross-section of 2 conductors, and what that would look like in real life, maybe if I go like this, would be something like this. These would be infinitely long, or long enough where they can be considered infinitely long. There wouldn't also be this connecting rod. This is just to hold them in place for convenience. But 2 isolated conductors, and they stick out of the surface like this, or in our case, like this, okay? And so we are dealing with the cross-section measuring voltage along here. So that's what we're studying. Now, let me move the camera for a closer look so you could see exactly what we're going to be doing in this lab. Now, as you can see, I have the equipment set up, but I want to point out that I'm actually doing this lab out of order. If we were doing this in class and not remotely, I would have you do this at your desks before you even take out the equipment. You're going to do a pre-data collection analysis. And so steps 1, 2, and 3, you're calculating the electric field in theory using Gauss's law around 2 cylinders, and then you're going to use the superposition principle to find the electric field of the 2 conductors. But I'll skip that for now, because I first want to take the data just again because it'll be more convenient from a video standpoint. So I'm on step 4, skipping ahead, and I'm going to take us all through step 6 where we disconnect the equipment. So rather than reading the instructions, you'll just see me doing the procedure on out. So what I've done is, as the instructions would have said, is I've taken the negative side, the power supply here. You could see negative terminal. I don't know if you could see that on your screen, but the wire comes and charges this conductor, this cylinder that goes up and down like this and through the paper. This side is negative. The positive side of the power supply, I don't know if you could see that little plus, the wire comes around here, past the meter, and connects here. So we've got a negative conductor, positive conductor. This voltmeter just connects to the negative side, and then I can move it along here to measure the voltage difference starting from here. Okay, so I'm measuring that voltage like that. So that's the setup. So now what I'm going to do is turn this power supply on and the voltmeter on, and I'm going to make the power supply adjust it so that there's a 20 volt difference between these two conductors. So I just connect it right to here, and I turn this dial until I get up to 20 volts. Now, as I said in the last video, I'm not sure how I'm going to give everyone their own data. So maybe in your data, you'll be starting with a different voltage other than 20. I haven't quite decided yet what I'm going to do. So just know that you might be dealing with 30 or 40. Look carefully in the sheet, the spreadsheet that I included in a Google Stream with your name. You'll find your name at the top, and the column will give you all your data. Okay, so 20 volts. Now, here are my analysis sheets. Again, I'm skipping the pre-lab analysis, and I'm going right here to taking this data over here. So what I'm going to do is, okay, at x equals 1 centimeter or 0.01 meters over here, I'm going to measure the voltage, then at 2, 3, on up to 11 centimeters. So what I've decided, and you would have implemented in the pre-analysis, is that this center of this conductor is at x equals 0. So I got my x-axis like this, x equals 0 right there. And then so this outer edge of the conductor is x equals 0.01 or 1 centimeter. Maybe I'll stay in centimeters for now, just because it'll be easier to say. This is 2 centimeters, 3, 4, 5, x equals 6 centimeters, x equals 7, 8, 9, 10. Then this outer edge of this conductor is at x equals 11 centimeters or 0.11 meters, with that being x equals 0. And the center of this conductor will be x equals 0.12 meters away from x equals 0. So at 1 centimeter, I'm right here. And what I do is I connect this on here, and I get about 19.9 or 20 volts, because again, that's the positive conductor there. So what I would do is write in 20.0 into that first box. Again, I don't need the voltage symbol because it's up here and it applies to all the numbers that I'm going to write down. Same with the meters here. Now I'm going to go to 2 centimeters. So that will be x equals 1 centimeter, x equals 2 centimeters right there. And looks like I'm approximately 16.3 volts. That's my voltage. So I'll write that down. Once again, you'll look up your own data here, and these numbers will be different. But I'm just showing you how this procedure is done. So that was x equals 1, 2, 3 centimeters is right there, and looks like we're at about 14.4 volts. So I write that down as my 3 centimeter entry. I go to 4 centimeters. 1, 2, 3, 4 right there. And I measure about 12.9 volts. So I'll write that down right there for the 4 centimeter, and then I go to the 5 centimeter, and that will be 1, 2, 3, 4, 5 right about there. And I get about 11.4 volts right there. So there's the 5 centimeter. Now I go to the 6 centimeter, which is right in the middle. I know that looks like x equals 0, or maybe here it says 14. No, this is x equals 0, so that's x equals 6. And what I have is about 10 volts exactly. So I'll write that down, 10 volts. There we are. And then we go to 7 centimeters away, which is right around here, okay, and I get approximately 8.5 volts, okay. There, Okay, now I go to 8 centimeters away. So here was 6, 7, 8, right about there. And I get about 7.1 volts. Okay, 7.0. Looks like it's lingering more at 7.1. Again, you know, you don't have to be exact because when you have a lot of data, those little fluctuations sort of average out. And 9 centimeters. So again, 6, 7, 8, 9 centimeters right there. About 5.4 volts. Okay. And then I go to 10 centimeters away. I've got my 5.4 and 9. 10 centimeters away. 6, 7, 8, 9, 10 right there. I have about 3.3 volts. I'll write that down. Okay, 3.3 volts. And then lastly, 11 centimeters away from x equals 0, which is all the way right here. Okay, and I get 0 volts. So I'll write that down. 0.0. Okay, so there's my data. Again, look to the Google Classroom stream and open the file that has all your names in it. Under your name, you'll find your own data. Okay, so now I want to go back and just say a little bit about this pre-analysis here before I close down here. So let's see if I can get this. So these are those two conductors, right? You can see they kind of match those points, you know, a little bit more or less. So that's the model. This is the model of this charged up. So in number 1, we are using Gauss's law to determine the electric field outside an infinitely long cylindrical conductor in terms of a linear charge density lambda. So lambda is the variable that you're going to use, and you just use Gauss's law to determine that electric field for one conductor, not both of them. And then 2, now consider 2 infinitely long conductors, each of radius 0.01, separated by centers of 0.12. As in the case of your wood board paper setup, assume that the left-hand cylinder is charged up to plus lambda and the right-hand cylinder negative lambda. If the center of the left-hand cylinder is defined at x equals 0, right here, this is x equals 0, right at the center. I don't know if you could see my pencil up there moving right there. That's x equals 0, as I mentioned, okay? And determine the electric field along the x-axis between the two conductors expressed using the expression for electric field of one cylinder derived from the previous step and the principle of superposition. So you got to think about somewhere like right here, for example, all right about there, there's an electric field caused by this positive, there's an electric field caused by this negative. Imagine the two arrows right there. Do you add or subtract those two magnitudes of E using that formula? Again, positive, negative. Do the electric fields add together or subtract in the middle based on their directions? And then you have to think about the symbol R in your formula. Okay, it is not the same for both. If this is x equals 0, but R is here and here, you want to get rid of R in both the formulas and only have x, considering x is 0 right there. So that's going to be a little bit tricky, but you'll think of it, you'll figure it out. And then 3, assume the potential difference from one cylinder along the axis is 20 volts. Determine the linear charge density lambda. Hint, be careful with the sign of delta V. Should you plug it in as positive 20 or negative 20 for the potential moving from the left-hand conductor to the right side? So if I start here, and by the way, there's no electric field inside these conductors. So the electric field only exists between, because the E inside of a metal is 0. So in this paperboard setup, the electric field is 0 all in here. It starts here and it ends there, and it's 0 in here also. So you got to factor that in when you're integrating. But as you're integrating starting here and ending there, thinking about the directions of the electric field in this region, between these conductors here, okay? What is the voltage come out? Positive or negative, integrating from there to there. So you plug that in and then you solve for lambda and you use that later in the lab. So that's the pre-calculation. As I said, I'm not going to go into all the details of all the calculations because we'll have plenty of class time where you can stay in the Google meeting and ask me questions on how to do all of this stuff here. Lots of analysis on this lab. So that's it for the data acquisition and a little bit about the calculations. The rest is up to you. So thank you for joining me, and I'll see you in the next physics lab video.